Okay, so today we're going to continue talking about vectors in 3 dimensions and specifically how to multiply 2 vectors together. So the first type of multiplication I wanted to talk about is scalar multiplication. And on this slide, they just remind you that there's 2 ways you can actually multiply vectors together. So the first is called scalar product, and it's read A dot B, that's the notation. You would have done this back in pre-calculus, and I think our book in pre-calculus calls this the dot product. So you'll hear me use dot product and scalar product interchangeably, but they mean the same thing. IB refers to it as the scalar product. Now, just for reference, the other way you can multiply vectors is called the vector product or the cross product. Those words can be used interchangeably. We're going to talk more about that tomorrow, but just keep in mind there's 2 ways you can multiply vectors together, either a scalar product or a vector product. The definition of the scalar or the dot product, these are your 2 vectors in component form. And A dot B just turns out to be A1, B1 plus A2, B2 plus A3, B3. The big thing I want you to remember about the dot product or the scalar product is that the result for this is a number. With cross product, the result is another vector. But with scalar product, the result is a number. So that's what you want to remember. Probably the most useful application for this is to talk about how to find the angle between 2 vectors. So let's come up with a formula we can use to do that. By the way, you'll notice at the bottom of the slide, it says on page 382, there's some important algebraic properties of the dot product. Look that over because you're going to need to know those properties and know how to apply them. They're real simple, just make sure you know them. All right, so let's come up with a formula we can use to find the angle between 2 vectors. So we're going to start with 2 vectors that are emanating from the same point. So this is really important. Make sure you see that, they both are coming from the same point, and we're going to call theta the angle between them. So to complete this little triangle I have on the screen, that third vector I drew would be B minus A. And in component form, B minus A, of course, would just be B1 minus A1 and B2 minus A2. And if you remember the law of cosines, or the cosine rule, which is what IB calls it, then the length of that side B minus A, or the magnitude of that vector squared, would be equal to the magnitude of A squared plus the magnitude of B squared minus 2AB times the cosine of theta. Pause for a minute, make sure you see that that's just the law of cosines. So if we go through and we put in the magnitudes for each of those vectors, so the B minus A, it's using B1 minus A1 and B2 minus A2, the magnitude would be this. And of course we're squaring it, so I'm squaring it here. Magnitude of A squared plus the magnitude of vector B squared minus 2 times the magnitude of A, magnitude of B, cosine theta. And of course the radicals go away. And if we were to distribute what's on the left side, do a little shuffling, do some cancellations, we would wind up with A1 B1 plus A2 B2 equals the magnitude of A times the magnitude of B times the cosine of theta. Remember, our goal here was to come up with a formula that we could use to find the angle between the 2 vectors, which we called theta. All we're going to do is just rearrange this and solve for cosine theta. Cosine theta is equal to A1 B1 plus A2 B2 divided by the magnitude of A times the magnitude of B. Now think about what is A1 B1 plus A2 B2. Just mentioned that in the earlier slide. That's just the dot product between A and B. And this formula is in your info booklet, so that's one you might want to refer to. But we're going to use it quite a bit in this unit. A couple of things to keep in mind. A dot B, if that equals 0, that means the vectors are perpendicular. Think about why that would be true. If A dot B is 0, that means the cosine of the angle between them is 0. Well, the cosine of 90 degrees is 0. So that's right where that comes from. So if A dot B equals 0, you know the vectors are perpendicular. And likewise, if A dot B is equal to plus or minus magnitude of A times magnitude of B, what that does is make this expression equal to 1 or -1. And that means that cosine of theta would equal 1, which would occur at 0 degrees, or -1, which would occur at 180 degrees. So if this result happens, that tells you that the two vectors are parallel. Okay, so let's do a couple of examples and just talk about what you would see here. So some typical problems involving the dot product. So if P is given and Q is given, they're asking to find P dot Q and then use it to find the angle between the two vectors. Of course, P dot Q, we just calculate the dot product, and that gives us a value of -4. Using our new formula for cosine of theta, cosine theta equals P dot Q divided by the magnitude of P times the magnitude of Q. So we just calculate the magnitude of P, calculate the magnitude of Q, that into our formula. That simplifies to -4 over the square root of 70. And then we could just do an inverse cosine. Now think about what kind of angle this would result in. If cosine is a negative value, you think about in terms of your unit circle, that would put you in the second quadrant, which means theta has to be an obtuse angle. So anytime cosine results in a negative value, the angle between them has to be obtuse, and it is. We get 118.56 degrees. Okay, let's look at another one. Find the measure of the angle between these two lines. So first line has a slope of -2. So if you think about that in terms of rise over run, -2 over 1, we're going to write that vector in component form as 1, -2. So that is the direction vector for that first line. Make sure you see that. X component goes on top, Y component goes on the bottom. Second line, if we rearrange it, we'll see it has a slope of 3/2. The component form for that vector would be 2 over 3. Remember, X on top, Y on the bottom. So again, we put that into our cosine formula. So A dot B divided by the magnitude of the two vectors multiplied together. And again, that's going to be a negative quantity, so the angle between them should be obtuse. And so we get this result. Occasionally, on a question like this, they'll specify whether they want the acute angle or the obtuse angle. So if they say the acute angle between the two lines, you would just do 180 minus this result if it happens to be an obtuse angle. Okay, next thing I want to talk about is something called vector projection. And I think you might have done this in pre-calculus a couple of years ago. I think you did a lot of this in pre-calculus, but I just want to make sure we go through and refresh on all of it because I know it's been a while. So what we're talking about, so we've got two vectors. Okay, so I'm going to call this point O, this vector OA and OB. Notice they both emanate from the same point. And I dropped a perpendicular from the tip of vector A down to vector B. Got some labels here, A and B. I'm going to call that point X, where vector A hits the other vector. So we call the projection of A onto B is the length of the projection of vector A onto B. So in this picture, the projection is the distance from O to X. That distance right there is our projection. Okay, that's the definition. The projection is a distance or a quantity. We read that as the projection of A onto B. And so using a little bit of trigonometry, SOHCAHTOA, right triangle trig, just make sure you see it. OX would be defined as the magnitude of A, vector A, times the cosine of theta. Think adjacent over hypotenuse. Well, we have a formula for the cosine of theta. Of course, we just learned it. So that would be A dot B divided by the magnitude of A times the magnitude of B. You'll notice we got a little formula here. So what happens to the magnitude of A? We're going to divide out. So the projection of A onto B would be the absolute value, let me explain that in a minute, the absolute value of A dot B divided by the magnitude of A, or I'm sorry, the magnitude of B. Now, I know this notation can be a little confusing, so just kind of bear with me here. Make sure you see what's going on. The notation projection of A onto B, first of all, make sure you understand that that means A onto B. Sometimes they'll switch them up on you, but this would be read, the projection of vector A onto vector B. And I know this is very confusing, but sometimes this is what IB does. The numerator, it's the dot product, and that does not mean magnitude. That means absolute value for this numerator. Okay, make sure you see that. Because remember, the dot product is a quantity. So this just means absolute value. And the only reason it's there is because the projection, remember, is a distance. So they're putting that on there just to remind you that it's a distance. Make sure if you happen to get a negative quantity, make it positive. On the other hand, this B is the magnitude. Doesn't mean absolute value, it means magnitude. I know that's very confusing, but that's what IB does. Really, magnitude is absolute value, length of a vector, if you want to think of it that way. It's all the same thing. There it is. Now, this would simply be the distance from O to X, the length of that projection. If we wanted to write the projection as its vector, if you were asked to write the projection vector, we would take that distance, A dot B, divided by the magnitude of B. Notice I took off the absolute value here because it could be negative. And this is the what? This is the unit vector in the direction of vector B. Okay? I know the notation is a little confusing, but it'll make sense as you go through the problems. So let's look at a couple of quick examples here. So if vector A is 2, 3, 1, vector B is -1, 0, and -3, they're asking you to do a few different things. Find A dot B, and then find the projection of A onto B, then go a step further and find the projection vector of B onto A. Now they switch that up on you. We'll talk about that. Let's just do A dot B first. A dot B, of course, that's the easy part. That's just our dot product. We get a result of -5. So the projection of A onto B, that's going to be the dot product of A times B, or A and B, absolute value divided by the magnitude of B. That's going to be absolute value of -5 divided by the magnitude of B. That gives us the length of our projection vector of 5 over the square root of 10. Now notice for part C they switched it up. They made it instead of the projection of A onto B, projection vector of A onto B, they went from B onto A. So that's a new calculation. So the projection vector of B onto A, this first part, of course, is just the projection, but notice I changed the formula a little bit because it's B onto A. So we're going to do B dot A. It's going to be divided by the magnitude of A. Take a look. B dot A, there's your dot product, -5, divided by the magnitude of A. But since we want a vector for this part, we're going to do the unit vector, 1, divided by the magnitude of vector A, times vector A again. So if you crunch all these numbers together, -5 becomes your numerator. Your denominator, I think this is the square root of 14, but times itself is just 14. Times vector A, we're looking for a vector here. Remember, vector A was 2, 3, and 1. So if we take that vector and we multiply it by -5 over 14, that gives us -5 over 7, -15 over 14, and -5 over 14. So that is the projection vector of B onto A. Okay, last question in this slide, or this PowerPoint, and this, I'm going to tell you right now, is a favorite of mine. This is one that IB likes, and I will probably put this on a test because you really need to make sure you understand how to do this. It's kind of a neat question. It says, use vector methods to determine the measure of angle ABC. So in this picture, they want us to find the angle ABC. So what I'm going to do is I'm going to set up a coordinate system. And you can set this up however you like. I tend to always put, I've got my XYZ system. I tend to always put the origin at that back left corner. The book might do it a little differently if you look up the answers, but that's how I set it up. In the end, it should be always be the same. And notice that, this is 2 units here, 3 units was the vertical distance there, and 4 units here. So that angle in blue, angle ABC, is what we're looking for. And notice, by the way, that C is the midpoint of this side over here. So we have to use vector BA to BC, because remember to use our cosine formula for the angle between two vectors. They have to emanate from the same direction. Okay. So let's come up with coordinates for points A, B, and C. So A would be 2, 0, 0. Make sure you see that. It's on the x-axis. So the x direction is 2 units, but the z, or the y and the z are both 0. Coordinates for B. So it's in the zy plane. So the x direction is 0. The y direction is 4. And the z direction is 3. How about for C? C is 1 unit in the x direction, because remember it was the midpoint of this side, which was 2 units altogether. So it's 1 unit in the x direction, 4 in the y, and it's on the xy plane, so the z coordinate is 0. Okay, so then we're going to write vectors BA and BC. So vector BA, use component form, tell me what BA is. We get 2, -4, -3, which is the B minus A. And then BC would be 1, 0, -3. So we're going to use our cosine formula, the dot product of BA and BC, divided by the magnitude of BA times the magnitude of BC. Once you've got the coordinate system and the points set up, the rest of it's pretty easy. The hardest part, I think, is getting that coordinate system set up. So practice that. Make sure you see what's going on. Okay, so we've got the dot product over the quantity of the two magnitudes. And then remember, of course, that's equal to cosine theta. Okay, think for a second, make a prediction here. Cosine theta is now a positive quantity, 11 over the square root of 290. So is theta going to be acute or obtuse? And it should be an acute angle because that was a positive result. Okay, and that's all for this PowerPoint, and then tomorrow we'll talk about the cross product.